Okay, this is final exam review number 3 for Physics 2111. Calculus based, first semester. It's time for us to talk about statics and dynamics. We've got static situations where we're in equilibrium, and then we have dynamics where we're not in equilibrium. We'll get to the dynamics part in a second, but let's talk about equilibrium. There's two conditions for equilibrium. We've got the first condition, sum of the forces equals 0. In other words, F net equals 0. Or the sum of the torques is equal to 0. Or T net, torque net, is equal to 0. Both of those have their implications. If you have F equals 0, then A has to be equal 0. And the same thing goes for torque. Alpha has to equal 0. What does that mean? That means that your velocity is either 0 or a constant, never changing, or omega is 0 and a constant. Both of those things, we need both. You can't have equilibrium without both things. If you only have one of them, you don't have equilibrium. Okay, now, if we're in non-equilibrium, then one or the other of these is happening. So we've got our sum of the forces is equal to A net, or our sum of the torques is equal to our moment of inertia times alpha. That means that your change in velocity is definitely happening, or you've got a change in angular momentum. Now, when would you not have a change in velocity? Well, that means that you're at your terminal velocity, or you're at your omega terminal. So you've got frictional forces that are impeding your forces applied. So you got applied forces, and then you have frictional forces, and they balance out, leaving you with these terminal velocities. However, if you're at a terminal velocity situation, wow, all of a sudden, these are constant, and you are back to equilibrium. Okay? So that's how the ball rolls. That's how the cookie crumbles. All right, so let's look at torque. All right, so we've got our sums of the torques. That's going to give you your total net torque. So your total moment of inertia times your angular acceleration, and that's this, right? Okay, now what if we just look at one of them? So we could take the torque of force 1. Well, that would be R cross F. Easy. If we say that R1 is equal to this, and our F is equal to this, then we can do the cross product. All right, and in the cross product, we did this last time. If you're doing the cross between I cross I, that gives you 0, okay? So, and J cross J, K cross K, all that. So you got to have these. But they're cyclical. So if it's I cross J, that gives you K. But if it's J cross I, that gives you minus K. So they're anti-commutative, whatever that means. Rx Fy minus Ry Fx is your result in the K hat direction. And because I didn't put any numbers in like we did last time, you can insert your own numbers. Maybe this one's bigger than this one, and then you have negative K hat direction. That could happen. Okay, so what if we're given the actual R magnitude and the force magnitude and the angle between them? Well, in that case, then it's easy. You can just do your torque in that case for that force is this. And that's nice, right? You can also go through and figure out, right? You can figure out the angles and all those things just from this. So you can come down and you can figure out what this right here gives you what R is, right? You square Rx and you square Ry and take the square root after adding them together. And Pythagorean theorem, that tells you what your magnitude is. You can get the magnitude of this. You can figure out their angle between each other, and therefore you can always figure out what this torque is. So one way or the other, you can skin that cat. Oh gosh, don't skin any cats. Be sure to label your coordinate system when you do this, okay? You guys gotta label the coordinate system. Here's your circle, and you're gonna do some torque action. Then you gotta say, oh, you know what? I want this to be positive and I want this to be negative, or vice versa. But if you don't do this, then the torques that are acting in the positive direction and the negative direction, how are you gonna know whether to make them positive or negative in your thing? And it doesn't matter which direction you pick. Pick one. And then if you end up with a negative, then you know that it was going counterclockwise. If you end up with a positive, you know it was clockwise. Okay? So label your coordinate systems, please, for your own sake. All right. Work and kinetic energy. Of course, that leads us to the work energy theorem. That's the combination of work and energy together, but it's really essentially work with kinetic energy. And first, let's talk about work. This is definitely work, right? So you do this, which leads us to this equation, okay? And initially, we could take the two vectors and multiply them together, cosine of the angle between them. That's doable. Now, technically, when you're doing this integral, the force could be a function of r, okay? So if it is, then you have to keep it with dr, okay? You can't pop it out front. If your theta is a function of r, again, you've got to keep that cosine in there with the dr. So that leads to a more difficult integral, right? Sometimes you get a more difficult integral in that case. Often, though, your force is a constant, and so is theta. So in that case, then you can just pop out the f cosine theta, and then you end up with this as your integral. So that's nice. So now let's talk about the relationship of work to kinetic energy. First of all, you have to remember you've got your linear kinetic energy and your rotational kinetic energy. So when you add these things together, that gives you your total kinetic energy. Okay, you got to add them together. So work net, this is the kinetic work energy theorem. This right here, work energy theorem. 1/2 mv final squared minus v initial squared is plus the kinetic energy rotationally. That you got to do both, okay? That will give you your work total, your work net. the amount of work done. So it's the way you got to do it. Now, I just want to make a little comment here. I final is not always equal to I initial. Okay, your initial mass and your final mass are probably going to be the same thing, but sometimes in when we're dealing with rotational systems, things change. Okay, and so your I final may not be equal to your I initial. So keep that in mind sometimes. Another way to get kinetic energy linear is to use the fact that mv is equal to your momentum. So then you can substitute in your momentum squared and then divide by m to get rid of the extra m that you have. So that works. And then the same goes for kinetic energy rotationally. You can do your angular momentum squared divided by the moment of inertia. Those work, and they're very helpful sometimes, especially if you're given the angular momentum or the regular momentum. All right, let's talk about power. Work or energy per time. Okay, so whatever you've got an engine and it's producing energy, how much energy does it do per time? That's the power. Okay, or how much work can you do in a certain amount of time? That is your power. All right, power is in watts. For those of you who don't know, watts. All right, so if it's energy per time or work per time, then you can take and get instantaneous power by doing the derivative of the work. That's if the work was a function of time, right? That leaves us with this integral. If we do a little algebra, we get that integral. And P could be a function of time. If it is, then you have to do the integral with P as a function of time in it. However, P is often constant. So if it's a constant, then you just have to do the derivative of the time, the integral of the time. Just basically T1 to T2 dt. That's it. That's easy. So the last thing here I have for power in this situation, we haven't looked at other ways of looking at power, which we will in a minute. But delta work over delta T is your average power. Okay, so if you start out at work final minus work initial over a certain amount of time, that's your average power. Okay, momentum. We've got linear momentum. Okay, linear. We've got rotational momentum. And then we have the impulses. Not personal impulses. These are impulses that happen due to forces and torques. Now, what happens if your F net is equal to 0 because A is equal to 0? Well, in that case, then you have an impulse that equals 0. But what does that mean? Delta P means P final minus P initial equals 0, or P final equals P initial, and that's a conservation of momentum thing. Same thing goes for torque, okay? If torque net is equal to I alpha, and alpha 0, well then torque net equals 0, and now we can say that we've got our delta L is equal to 0, meaning that L final equals L initial, and we're again left with conservation of momentum. It's just angular momentum this time. keep in mind, P final and P initial can be in 2 dimensions. All right? So if they are 2-dimensional, you can't just do 1-dimension stuff. You have to do this dimension. You have to do this dimension. Do both. Please do both. Angular momentum. Angular momentum gives us this I omega squared is equal to I final omega squared. Again, often the case is that I initial and I final are not the same. That you just have to deal with, right? I mean, it's easy. It's not too hard. You just get the different I's for the different finals and initials. That's okay. All right, potential energy. We only get potential energy from conservative forces. All right, I'm going to kind of go off here on a little bit about conservative forces. Why do we call them conservative forces? We call them conservative because we get the energy back. They conserve our energy. It's like a bank. You put your energy in the bank, it conserves it for you. It doesn't grow interest, but it definitely conserves it for you, which is good enough. Then when you try and take it back, you can get that energy back, right? You get it back later. So the greatest example of this is hydroelectric power, where you have a dam storing water up in the mountains. Gravity is going to let us bring that water down, and we can take energy from that water. So it's gravity, gravitational forces. Gravity is one of the conservative forces. So we're lucky with that. All right, so they're easy to spot. Why? Because they don't care what path gets taken. As long as they get from one point to another along the potential, what do I want to call it? Potential gradients, equipotential lines. Okay, so you don't know what I'm talking about, but what if there's a mountain? Have you ever wanted to climb a mountain? Oh yeah, me, all the time. And they have this thing where here's the top of the mountain, and as you go down the mountain, there's these different rings, and you can tell where the height of the mountain is. This is called a topographical map. These are equipotentials. Equipotential lines. Okay? So if you're here and you walk along the line, you don't gain or lose any altitude. But if you go this way, because you want to go up the mountain, you're going to go up to the top of the mountain, well, you are gaining because you're crossing the equipotential lines. You're going to the top of the mountain that way. All right? So that is where you get your potential energy from, by crossing the equipotential lines. All right? So that's it for gravity, topographical maps. We do the same thing for electric fields. All right, similar stuff. Next semester. Okay, so we're going to get from A to B, and it's obvious that it doesn't matter which path we take. Whatever path we take to get from the mountain to the top, it doesn't matter. We could go this way. We could go this way. No matter what way we go, we're going to get the same potential energy difference. Okay? And we get that energy back when we go back down. So we're putting energy in the bank. There are two forces that give us this potential energy back. Gravity and springs, so far that we're studying. All right. electromagnetic forces do too. When we did the collisions in the cars, we wanted to save energy, and we didn't want the cars to smash into each other, even though they were kind of colliding. We wanted to make sure that they didn't really smash into each other. We used magnets, and the magnets did their thing. They gave all the energy that we put into them, they gave it back. Not all, but just about all. So there's two potential energies for gravity. We've got our MGH, which is the one where, basically we're on the surface of the Earth and we're dealing with that. Or we could be dealing with orbitals and things that are going outside of, higher radiuses than just the radius of the Earth or Mars or Moon or whatever you happen to be on. So these can be negative. You're in a hole, basically, here. All right? You're in a gravitational well. Your height could be in a well. You could have dug a hole and stuck something into the hole, and you want to know what its potential energy is. Well, you got to provide energy to get that thing out of the hole. All right? So you have negative potential energy. However, springs are a little bit different. No matter what happens, if you stretch the spring away from its equilibrium point, in other words, if delta x gets greater than 0, then no matter what, you are gaining potential energy, okay? No matter what. It's always positive, okay? There was something else that I wanted to say about that. Oh, the reason springs, don't tell anybody this, but the reason springs are springs is because of the electromechanical bonds in the material of the spring. Okay? So, secretly, this is a secret. It won't be on the test, don't worry. I just want you to know this. Springs have nothing to do with, they're springy because of the electromechanical bonds. Okay, that's why they're springy. So again, we're dealing with electromagnetism, just like the magnets. That's given us our spring potential energy that gives us the conservation law, and it all comes down to being electrical bonds. All right. Conservation of energy. So physics, I've said this probably 10 times, maybe once, at least twice, is the study of energy, okay? And energy is all of it. Mass is energy. Charge is energy. Information is energy. You name it. Everything's energy, okay? So when we're able to do accounting for energy, it's so fundamental, okay? It's like the most fundamental thing that we could possibly be doing. We're counting up, we're basically doing accountant's work, okay? Accounting. I don't know how to spell accounting. I just ate dinner, so my glucose is overwhelming my brain. Okay, whatever. So you're handling it with accounting, and that's easy. We like that. That's why conservation of energy was a big deal for us, because we could get away from vectors and forces and all that stuff and just do accounting. So this is the easy part, okay? Accounting. We have an energy total, and if we don't have any friction, our energy total is equal to the total mechanical energy of the system. The total mechanical energy is all the kinetic energies plus the potential energies. Okay, but you got to keep in mind your kinetic energy is both the rotational kinetic energy and the linear kinetic energy. Okay, so you gotta remember that. Now, with friction, things change a little bit, because now our energy total is our mechanical energies plus all the work that we lose. This is basically non-conservative forces, and so it's work due to frictional forces. They don't want to just say friction. We call it non-conservative. It's all the junk that is going to take energy from the system and not give it back, right? If it's conservative, it's a potential energy and gives it back. If it's non-conservative, it's not, and it takes it out. Well, frictional forces are the things that take energy out of your system. So no matter what happens, your total final energy is going to be equal to your total initial energy, but you have to include all the energy that was lost to your non-conservative forces. Okay. Our energy total mechanical is then not conserved, because these are conserved, but this is gradually sucking all the energy out of the system. Okay? Our work due to non-conservative forces always gets bigger as time goes on. Okay? Always. And that's why time is time. That's one of the reasons for the arrow of time. So, what about moment of inertia? Okay, so we're going to start doing some rotational stuff here. Moments of inertia. We've got inertia that has a mass in linear situations. Well, there's the rotational equivalent of that, and that's called the moment of inertia, which is kilograms per meter squared instead of kilograms. So, it's not one goes to the other. They go back and forth. One's the rotational, one's the linear. All right? So how do you figure out what your moment of inertia is? Well, there's this method, all right, which, I don't know. Have you guys had to do that method really? Not really. There's this method. I don't think we've had to do that either. I want you to know it, understand that that's what you would do. But mostly what we've done is this method. We did it in our lab. We figured out the moment of inertia of a disc or the platform. We did the disc, and then we had another moment of inertia like of the hoop. We measured experimentally this, and then we subtracted off this one and this one so that we could get our I3, which would have been the hoop. Okay, so we've done this before. That's the same thing. Okay, so there are usually many parts of a system, and all of those different parts have their own moments of inertia, and so that's why that works really well. Okay, what about the parallel axis theorem? We had a test question on this, and everyone did pretty well on it, actually. So we've got I for the parallel axis is equal to I of an axis through the center of mass, and they have to be parallel. So you can't have, how would we do this? I'm going to draw this guy, and we've got an axis right down the middle. And if I wanted to do an axis here, that's not going to work. This is not a parallel axis. It's called the parallel axis for a reason. Axis theorem for a reason. Yeah, it's not going to work. You'd have to have your parallel axis be somewhere that's parallel. Okay? So if you were to do this center of mass and then do this other one, that's fine. That works. Okay? So it has to be parallel. And then you find the distance between those two things, right? There's our distance between them. And you've got your moment of inertia for the center of mass. You take your mass of the object and you multiply it by the distance squared. You add those two things together, and that is your new parallel axis moment of inertia. Okay, I think you guys get that pretty well, so let's move on. Oh, here's the one where we're talking about rotational power. I must have missed it earlier, so I want to talk about it. Linear power, if you know your linear velocity and you multiply by the force that's happening, you can get your power out of the situation, okay? Well, the same thing goes for your torque and your omega, all right? And these guys are most often in the same direction. We try and make these in the same direction too, otherwise it gets complicated. Now, keeping with the moment of inertia thing, rolling and whatnot, we could have a ramp. We've got a cylinder rolling down the ramp, and it's doing its thing. Everything's working out great. We found that the acceleration of the center of mass, okay, is this equation, this one right here, for any object, all right? But you have to know the object's moment of inertia. Its center of mass moment of inertia as it's rolling. So you figure that out, and you can stick that in, and then you can get the answer. So if you're using a cylinder that has this moment of inertia, when you plug that in, make sure you plug that in, do it yourself. You can pause the video and do that. Make sure you get 2/3 g sine theta, okay, when you do that. You can have a hoop, okay, or I sphere. What is a sphere? I think that's I sphere is equal to 2/5 mr squared. I think that's it. I'm going off the top of my head. If I'm wrong, look it up. If I'm wrong, that's fine. But figure out what your acceleration of the center of mass for the object is. Another thing that we did find is that there has to be some kind of friction in the system because it's rolling without slipping, right? And we understand that now, right? We know that if you slam on your brakes on the ice, your tires will skid. You are now doing mu kinetic. But if your tires are rolling with the ground, they're touching the ground and they don't slip. So rolling, even though you're moving, you're doing static friction. At any rate, we found that mu static has to be greater than or equal to 1/3 tangent of theta for things to roll, okay? Because they're not just sliding anymore. So then we did this thing with the final velocity for the cylinder. We found it to be this. For a hoop, it's this. And you can ask yourself, well, what is it for a sphere? Okay, and that's a good question. All these are great questions that might be asked. Okay, so next is gravity. I think we're going to save gravity for class. I may or may not record a video for that, but at any rate, all these videos is wearing me out. It's not easy to produce them, so I hope you enjoy the videos as much as I have, and I'll see you guys soon.